off to the races. So I'm going to be talking, so you can certainly talk with each other as well. As we talked about the several different, go ahead and insert my pencils. The first step to everything is to find the total voltage, which will be given, and that is the total voltage. So it's going to be a little bit difficult because this problem is so wide. Next thing to do is to find the total resistance, and this is where you've got to be careful. We have these two resistors in series that are inside the parallel. So since they're in series here, I could add them together. So 12 plus 14, I'm just going to show that it's 26. And then I have to add these three in parallel. So I have 1 over 8 plus 1 over 10 plus 1 over 26 to the negative 1. And I'm just going to go ahead and give you the calculation for whatever that ends up being. That ends up being 3.796. And then we have to add, so this whole thing is 3.796. We have to add 2 plus 4 plus 6, because those are in series, and we get a total resistance of 15.796 ohms, which goes right here. Third thing we have to do is figure out what the total current is, and the total current is equal to the total voltage divided by the total resistance, and that equals, for this one, 3.039. Make sure we got the 3 decimal places, and that goes here. Reminder here that there's the only column. What's the only column that should actually have all I guess I'm already showing it here. All the powers added up should equal the total here. None of the other ones should have that. Next thing to do is to draw the current. People say, I don't know what to do after this point. And I say, did you draw the current? They're like, no. And I'm like, well, of course you didn't know what to do. It doesn't matter really which way it's coming out of here. I'm drawing, the current is coming out of here. Okay, it's going into there, it's coming out of here, in no certain order. So everything that is in series with this battery here, the 2, the 4, and the 6, those all get that current coming out, which is the 3.039. Don't think of it like the 4, and then the 6, and then the parallel, and then the 2. Think of it like we have to deal with all the series as if they're the first floor of our shopping spree before we can do anything else. Once I draw the current, whatever resistor has red in it means that it gets that current. So this gets 3.039. This also gets 3.039, and this one 3.039. We're on the first floor of our shopping spree here, and we had 48 volts that we had. The next step is to figure out how much did we just spend by going through the series. And we have V equals IR, so we can multiply that, that, and that. And these will give us how much we've spent at each of them. Just to, first one is 6.078, so it's as if right here we have spent. You say, wait a second, that's at the end. No, it's all moving at the same time. Simultaneously, out of the 48, we spent 6.078. We also spent 12.156, and I'm putting negative there because I'm just trying to show you we spent that much. We also spent negative 12.156. Basically, I'm keeping my records here to figure out how much do I have after I've spent it all. And in the last one, we have spent the most, which is 18.234. And so I'm keeping track of how much is being spent. I had 48. In the series, I have spent each of these, and if I want to figure out what is left over, so whatever voltage is left over, that's what has to be going into the parallel. I subtract each of these, and I get 11.532 volts. Okay, so here's why I want to kind of transfer to this drawing here. So the drawing and that, just because it's a little bit more zoomed in, not so much going on there. We know going into the top, red is current. We have 3.039 amps going in, just into this parallel. We also have calculated how much voltage we have left to go into here. It is also going in. At this point, it's about knowing sort of Kirchhoff's laws, or in a way. Let's first deal with voltage, because whenever we're thinking about parallel, you should be thinking about voltage, because if you know what the voltage is going in, it gives you an idea. So here is what's going on. From this point there to this point there, we need to spend each of these, from there to there, from there to there, and from there to there, we need to spend 11.532. Why? Because we already calculated how much we spent before, so we have to spend across those. Every parallel path from one side to the other will spend 11.532. So the question is, from here to here, I have to spend 11.532. There's only one place to spend it. So how much am I spending at that one place? Yep, 11.532. That's how much voltage is going through there. Okay. This also has to spend 11.532, and there's only one place to spend it. And so that also gets 11.532. And we also have to spend 11.532 from here to here, but there are two stores, and we do not know how much is being spent at that. So we're going to say we don't know at this point. So you're saying, well, what do we do? Well, we need to fill in the table more. We have just realized that the 8 ohm here, there is 11.532 volts going through there, and there's 11.532 volts being spent there. One of the whole goals is that the other thing we have here is that we have the current. We know the amount of current that is going in is different than voltage. The amount of current that goes in is going to split up in some manner, but it's going to come out again at 3.039 amps. If we can figure out how the current splits, then that's beneficial to us. And how we do that is that we have how much voltage is going through the 8 ohm resistor, and we know the resistance of that. So we're going to go ahead and figure out what is the current of the 8 ohm resistor. If we know the voltage is 11.532 volts, and we have a resistance of 8 ohms. We do that, and you get 1.442 amps. So we know out of the 3.09, how much is going through the top? 1.442 amps. Now we need to figure out how much current is going through the middle here, and so that would be the current through the 10 ohm resistor. We have, once again, because there's only one place to spend it here, 11.532 volts is being spent now through the 10 ohm resistor, and there you get 1.153 amps, which means 3.039 going in. 1.442 went to the top. 1.153 is going through the middle. Once again, since I'm recording, you can go through this slower. And we do not know how much voltage is being spent in either of this, but we have just calculated something very important here. We figured out how much is going through the top and through the middle, and so whatever is left over, so 3.039 amps minus 1.442 amps minus 1.153 amps has to be going through the bottom path. And that number, hold on, is 0.444 amps. And that is what is going through the bottom. So we know in the 12 and the 14, 0.444 and 0.444. At this point, we can calculate how much voltage is going through here, and I want to show you, once again, in the beginning, I said here, from this point to this point, 11.53 volts has to be spent. 11.532 volts. 11.532 volts. If we calculate the voltage here and here, that within rounding should add up to 11.532 volts. I'll put the numbers in front of me since I didn't do that here. So 12 times 0.444, 5.328, and 14 times 0.444, 6.216. So if we add those two together, 6.216 plus 5.328, within rounding, it's about within a tenth of a volt here, because we had to do rounding along the way, means that we have found how much voltage is going through the bottom. At this point, you have enough to calculate the power, and the power is P equals IV. All of these added up is this number here. Sorry. All of these added up is this number, and then your power, so if you take your total current times your total voltage, we should get total power, which is this number right there. If those are within a watt at most, then you can agree that they are the same, and then I ask you to put the one that is based on your adding in there.